Hello, everyone, and welcome to another series in machine learning for disease prediction. This series is sponsored by Simplilearn, and I'm Dr. Yuana Thiessen, and I'll be guiding you through this series of machine learning, starting with the basics of the data science fundamentals all the way to modeling the data and showing you how machine learning can be used for risk prediction as far as cardiovascular disease is concerned, and how this is helping to make a difference in how cardiovascular disease and other types of chronic illnesses are being helped by the practice of machine learning. So cardiovascular disease, it still is the number one killer. Over 12 million people die from cardiovascular diseases every day. And what we have learned so far is that some of these deaths are preventable. And so there is quite a lot of research that is going on, both in the lab and in the field, and as we will see here, in the area of data science that is helping to make a difference. And so there's the famous Framingham Heart Study, started way back in 1948 and continues to today. It's in its third generation of participants. But this study was instrumental in us beginning to collect data specifically for studying heart disease. It's now been extended to study other kinds of diseases. But we can use the data, which is now, I amassed several thousands of participants, and we can use this data applying machine learning techniques to help us understand the disease, how it is manifested, what are the signs and symptoms of the disease, and then use that also to predict the potential presence of the disease in asymptomatic patients, and so help to guide them such that they do not develop the disease. Also help those who have developed the disease, what steps can be taken to reduce their risk of dying from the disease. So machine learning has been very helpful to medical practitioners in the field of cardiovascular disease as well as other diseases.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
So when I talk about the steps in the machine learning project that we will be embarking on, I want you to keep these 5 steps in mind, right? I've used the acronym of AFTERS to help you remember. First there's the acquisition of the data or acquiring the data. Then you will filter and clean the data. And then there's transforming the data, then you explore the data, then you split the data. So I think of it kind of like you're following a recipe. So of course you first have to gather all the ingredients together. That's the acquire or the acquisition of data stage. Then next is you will be filtering your data, similar to if you are baking a cake, you want to filter and sift your flour and other dry ingredients to make sure that it's clear and clean. And so too with the data, we want to make sure that the data is accurate and that it is suitable. And then, when you're baking a cake or even making bread or, any kinds of recipe, sometimes it requires you to transform the ingredients. And similarly, when just like you would be melting the butter, taking it from solid to liquid, we need sometimes to transform our data from text data to numerical data, or transform feet to meters. There's always some kind of transformation of our data is concerned, so that we have accurate data and we have a uniformity of the data that is suitable for our model requirements. Then the next step is, after we've sort of transformed the data and we have it uniform, we do an exploration of the data. And this is where you get the understanding of your data. So there is some exploratory data analysis. There's lots of generation of plots. So for visualizing, so there are some patterns and certain trends in the data that you will begin to understand as you explore your data, and that will guide the kind of machine model that you'll be able to build from your data. And sometimes you will go back to the transformation or even the filtering stage. So there's kind of a cyclic process here until you get your data in a state that is just right for generating the model. And then once you get to that state, there's splitting of the data. So you first are going to split into the X data, the X variables, and the Y. That's provided that you are doing a particular kind of machine learning model, meaning that you're making models where the labels are important, or maybe not, but you will require splitting. And then there's another split that you do more of a horizontal split. So you split your data more, sometimes 80-20 or even 70-30, so that you can save some or reserve some for the testing. So the first 70% you'll use for training your models, and then the 30% you'll use to test the performance of your model and evaluate it, and then decide how and when or if you need to make some changes so that you can improve the performance of your model. So those are the five main stages. There are others that are involved, and we'll see those as we go along. But you want to remember acquiring, filtering, transforming, exploring, and then finally splitting up the data before you start modeling. So acquiring, data acquisition is the first stage of any machine learning project. And so there are various ways by which you can acquire the data that you need. It's important that that data is suitable, of course, to the problem, the business problem, the societal problem, whatever the issue is, the phenomenon that you are trying to model or to learn or to gain insight from. You want to first make sure that you have suitable data. So you can get the data by scraping the internet. You can extract that data from another source. You can be involved in your own data collection in terms of whether it's a survey or some type of other activity, or you may have to combine data from different sources. But these are ways that you can actually acquire the data that you need. And so sometimes it's just simply getting the data from the internet, as we will be doing. My data acquisition stage is actually quite short because I am using data that is available when it comes to the Framingham Heart Study data set. It's quite popular. A lot of people use it. You can get it from off GitHub. You can get it from many different sources. You can just Google Framingham Heart Study data set, and it'll show up. And so I've downloaded it and saved it to my computer. And so I'm going to, of course, first, before I can load it onto my notebook, which here is the Google Colab notebook. And so I need certain tools, right? So these are the tools that we need to start our, project. And so first we will have the importing of Pandas, Numpy, Matplotlib, Scipy, Sklearn, and Seaborn. So Pandas is for the data frame, Numpy is for numerical type activities, Matplotlib is for our graphs, basic graphs and charts. Scipy is for statistic, Sklearn, as well as, Seaborn is also for graphing, and Sklearn is for when we actually do the modeling. So we will import those by running this cell here. And once that has run, we will then I need to install this PyRead stat, because my data set is in the SAV form. Now yours may be in Excel or CSV, so you would use a different function here, method here for loading your data set. But this is what I'm doing. So now we have all of these modules. Now I can install my PyRead stat module, and then I can load my data. So for that, I am going to make sure that my data set is actually loaded here. And so I'm going to make sure that I'm loading this data set that I need from my computer, and here it's going to tell me that this is a temporary load, and that's okay because we can always load it again. So now that I have all of these in place, now I can go ahead and actually read my data set into my notebook. And so once I've done that, then I can take a look at my data set by looking at the first 5 rows. And so that's what the dot head method does. Then I can see, I'll give an example, just a snapshot of what is contained in my data set in terms of the types of columns or types of features, and then what the rows look like. So it's showing here that I have 34 columns in all, but we don't know how many rows. So that's where the dot shape comes in. So if I do that, it says that I have 4,578 rows. The first value is the number of rows, and the second is the number of columns, as we saw here. Then if I want to just take a more detailed look at what is in my data set, I use the .info method, and that gives me a list of all of the columns in my data set, as well as whether those columns are filled, contained information or not, to the extent that, so we have 4,578 rows. And so we see age all of the age rows are filled, but not so much with cholesterol. So anything that is less than 4,578, we know that it's missing some values. Also, this .info gives you information about the type of data that's in each column. So some are floats and others are categories. And then the final thing we do when it comes to just looking at our data is using the .describe method. So I can show here in terms of what the average value is for all of the features. And then I can see what the minimum value and the max and 25th and 75th percentile and so on. So for that, I've used the .describe. And so I've transformed the matrix so that it's in a different arrangement. And then I've also applied this display.float so that I can remove the extraneous numbers after the decimal point. So that's what we would do when it comes to, just acquiring the data and taking a look at it and making sure that it is what we wanted it to be. So after you have acquired your data, this is where you will do the filtering of your data. And the main idea of the filtering is to get rid of the errors, duplications, any kind of data that doesn't belong, that is not going to be helpful to you in your modeling process, as well as looking for outliers and any kind of extraneous type of info that we may have to make some, do some transformation to, depending. And so we would look for outliers, of course. Then we'd see if, there are values that are entered that don't belong. We also want to get rid of duplicates because that could cause bias and inefficient modeling. And we also want to look for invalid data, right? So if it's supposed to be measurement of heights, then we want to make sure that it's all numerical and that there is no text in there, etc. So that's what the filtering is in a nutshell. So let's do some filtering of our data. So for the filtering, I noticed that we had, first of all, when I did do the dot describe, now that, mind you, that gives you only the numerical or values that are labeled floats in this case, not the ones that are categorical. And if we looked at the dot info method, right, we'll see that there is, as far as the 7th column or the 8th column is concerned, there's a PID or some kind of ID, and it's labeled as a float, but that is, it's not information that we can use for our modeling. And then there was another ID measurement somewhere in here in terms of the ID type. So I wanted to first go ahead and remove those 2 columns. So I'm using the dot drop method. I put the 2 column names into square brackets as a list, and then I identify the axis 1 to note that these are in the columns ID. So once we do that, I reassign that back to the data frame. We can do simply do an in place equals true as an option. So I do that, and now I've gotten rid of that. And if I do dot shape again, we would see that now we have actually 32 rows to 32 columns now, and we do have 457 rows. So we have, so when I get rid of the columns, the PID and the ID type, and I check the dimensions of my data frame, I can see that instead of 34, I now have 32 columns, and I still have the same number of rows. So now we've gotten rid of those, invalid in pieces of information. They're not important to our modeling. Secondly, now we want to look for missing values, and that's where we use the is null. So what that'll do, it'll show us wherever there are values missing, it will say true. If the values are there and they're valid, whether they're valid or not, as long as there are values there, it will say false. So we want to get a count of all the missing values in each of the columns. So we would use the is null, and then we would add the dot sum to it. So it'll tell us for LDL cholesterol, 67 values are missing, for diabetes status, 11, and so on. And if I want to get that as a percentage of the columns of the total number of observations, I can then divide by the length and multiply by 100 to get a percentage. So for the LDL cholesterol column, 1.464% of the values are missing. So that's how we would identify the missing values. Now, there are other ways we can look for missing values, and that is using this missing go module. And once I import that, then I can use the MSNO to get a visual of my data frame. So I would use MSNO.bar, and I would put the name of my data frame into the as an argument. And that is going to give me this lovely bar chart where we can see in anything that is not the length of the other bars, we know that there are some missing values. Now, our data set does not contain a lot of missing values, so the bars look almost identical. But just as an example, alternatively, we can use the dot matrix method. And what that does, it gives you a printout of the matrix where when a number or value is missing, you will get a white space. Not much missing, so not much to look for. Then finally, when it comes to missing values, visualizing missing values, we can use a heat map, right? We can now do the MSNO heat map, and that gives us some idea of the the correlation between the missingness of one column relative to another. And so we can see that, of course, certainly glucose times HDL. So this is a interaction column or feature created from the glucose and the HDL measures. And certainly that is going to be correlated with HDL cholesterol because it's generated from that. And so we can get an idea in terms of the relationship between the missingness of one feature relative to another, because that's going to determine how we deal with these missing values, right? So depending on the nature of the missingness, whether it's related to another column or not, or whether it's related to the target column or outcome variable that we're trying to model for or predict, then we're going to treat those differently from those whose missingness are not correlated with the target variable. So you want to bear those things in mind. So when it comes to dealing with the missing values, there are a number of things that we can do. Now, we are in this case, for example, we're going to delete the rows from 2 of the columns where they're missing values. In fact, not delete, we're going to impute, or we're going to fill those with the mean of that column. So in the first place, when it comes to the LDL cholesterol, we're going to fill in all the missing values with the mean for the LDL cholesterol. Similarly, we're going to fill in all the missing values for the fasting blood sugar with the mean of the fasting blood sugar. And so once I run that, that's what's going to happen. And so if I do that now, I can see that when it comes to LDL cholesterol, there is no longer missing values, as well as for the fasting blood sugar. So they've now been filled in. And so for the other columns where there's still some missing values, because the percentages are so low, we can go ahead and simply drop the rows that contain missing values. And that's what we use the drop NA for. And we apply that to our data frame and then reassign it back to the data frame. We can also alternatively do an in place equals true so we don't have to reassign it. It will actually happen to the data frame itself. But we now have that. And then if we check for missingness, we see now all of our columns are complete. So we are good to go as far as missing values are concerned. No more missing values. That's one of the ways. There are other ways. Python and Sklearn comes with some very fancy modules or different programs, algorithms that you can use for filling in missing data, doing whether it's the mean or the median or the mode, depending on what type of variable it is. But these are some of the basic ways. You can either fill in with the mean using the fill NA, or in this case, if the missingness is usually not more than 10%, then you can go ahead and drop those columns. So now we have accounted for all our missing values. And so the last thing it would do for filtering as far as our data set is concerned is to check for any duplication. and our data frame. There are no duplication as far as the entire rows are concerned, right? There are no two rows that are the same. Now, if we wanted to look for duplication by way of, say, one column or a group of columns, then we could use the subset inside of the duplicates method, right? So this is giving you info here about this method, and it's showing you that, by default, there's nothing that you will be using as kind of a subset. So it's looking for the entire row, and if it does find it, it will generally keep the first, and you can stipulate whether you want to keep the first or keep the last. And so that's because we don't have any duplications, then we can't really we don't have to use this. So that's what we would do for filtering. We would first look for missing values. In this case, I also got rid of firstly those PID numbers because they were not important to our modeling. Then I checked for missing values and I dealt with that. And then I checked for duplicates and I also dealt with that. So that's how basic filtering method would occur. So the third step in our machine learning process is that of transformation. And remember, these steps can be fluid. There's no hard and fast rules because, as you will see, there's there might be some filtering going on in transformation and vice versa. But essentially, transformation is mainly about changing the values into a form that is suitable for modeling. So first and foremost, the models can only accept numerical values. And so if we want to use a certain column, a certain feature in our model, our algorithm, then we would have to change any text into a type of numbers, whether that's integers or floats. So that's the main model transformation that happens. There's also sometimes, some mapping going on where we may be changing a continuous variable into some kind of a binning. Also, there is, of course, the formatting when it comes to date. If we're doing time series type of modeling, then we would want, usually when we get the data set, it comes in as text as far as the date values are concerned. And so we would have to convert them to the special Python date type features. So those are some examples of the data transformation that we do when it comes to machine learning. There are quite a few more, but we'll just touch on some of the basics for now. So the transformation that we're going to do here. So first, let's remind ourselves what kind of data we have in our data set. And I think I made some changes. So let me go back to, I'm going to run all of this again just to make sure I'm giving you everything. So this is reload the data. Then we did, what were some of the other changes? We got rid of these IDs. Then we looked at the missing values. Then we actually filled in those two columns with the mean, and also dropped other columns with missing values. So that's the main steps that we've done so far. So now with the data transformation, so if we look at our data set as far as the data frame is concerned, we see we have floats and we have some categorical variables, some of which should be categoricals, others possibly not. But so for example, we have these date values that we're going to need to take care of if we want to use them in the model as they are intended. Also things like gender. Now here it is a float, so we also look at this diabetic status. So that's if we saw what the categories are. So it's non-diabetic, diabetic. So just two categories. So this is labeled here in the data frame. If I can find diabetic status, right? And it is categorical here. So, right now it's fine using it as categorical. We can then see what those values look like in terms of if we wanted to get an idea of the distribution of diabetics in our data set. We would do values counts, and that would give us what that looks like. If we want to do it as percentage, we would do normalize equals true. And so 0.035 are diabetic, very low percentage of diabetics in this data set. But if we wanted to convert that to a numerical, say we want to include it in our model, then we can use the dot replace method. And how that works is you identify the column using calling it out with the square brackets, and you dot replace, and inside of that method we're going to include the categories that are the original feature, and then as a list, and then we include another list for the values that we'd like to replace these with. So if I run that, so now I'm reassigning it back to the data frame, so it's actually changing my data frame. And then if I do the unique, that's what happens. Now, if we were to run this again a second time here, then we would see that instead of saying non-diabetic and diabetic, it's now saying 1 and 2. So that's one of the other ways. This is a second way that we can do some kind of data transformation, and that is using the Pandas get dummy. And it's usually used when we have these categorical variables that we want to change into some numerical values so that we can now include them in our model. And so what the get dummies does is actually going to give each of the category its own numbers. And so if we ran that, we see here now it's doing 1, and wherever there's that person is actually diabetic, you would get a 1 here, and then that person would be a 0. So it's taken that one column and split it into 2 columns. And so now we see whenever there's a diabetic, it's 1 in this first column. And if that person is now, if that person is not diabetic, then the 1 would be in a different column for the diabetics, for the non-diabetics. So that's how that would work. Now, if I were to say use this with a different column, that maybe we can do the age group feature. And if I ran that, so the first thing we would do is let us see what are the categories for age group. So if we did that, we put our age group column in here, and I want to make sure that I get the name correct. So I would do age group, and I would put that in here in place, and that would give me, so there are the age groups. So there's 26 to 40 and 41 to 60 and 70. So 1, 2, 3, 4, 5 age groups. So we could go ahead and we could do something like we did here for the diabetics column. And so we put that in there. We now are going to replace our age group. So we have all of these as the various column headings now. Oh, and we're going to use that here. And this is also going to be age group as well. And so for these now, what we're going to do is we're going to replace these with actual text that we can use. So less than 25, we're going to call these the young, the youth. Let's say IOUTH. And then the next grouping, we're going to say young adults. And then the 41 to 55, we are going to call these adults. Then for 56 to 70, we'll say middle aged, and then we will say old, right? So those will be the categories that we are replacing them with. So we can run that. And now if we were to do a values count, we can see how those are distributed in our data set. And so there we have it. We have adults, young adults, middle age. And if I wanted to do a plot of that, I would do kind equal bar. So that's using the built-in Python plotting method. And that would generate this lovely plot so we can see the distribution. And so that's how that would work. And now if we also wanted to say, do the get dummies, what that's going to do, it's going to create a new column for each of our categories. And if we did that, now we have 1, 2, 3, 4, 5 columns. And of course, here, this person is adult, so it's 1 here and 0 elsewhere. The first person is a young adult, so it's 1 there and 0 elsewhere, and so on. So that's what this get dummy does. It's going to create an additional column for each of the categories. So that's one of the ways that we usually convert categorical variables to numerical variables. Now, you want to be careful that there aren't excess of categories, right? Because then you have the curse of dimensionality as far as your model is concerned. So we want to avoid that. There's other method here we can do is to use the label encoder. And so we import that from the pre-processing module. And once we've done that, we create an instance, or we get a blueprint of that algorithm. We assign that to the name LE, and now we can use it here. We're using the model here, and we're going to fit it and transform it on the data set for gender. And I already did that here, but that is what, if we took a look at this column as it was originally in the data set. So let's do a value count on that. And that will show us how many males and how many females. So it's giving us that 2 and 1, and I'm not sure which is which, but we can also always check the data source and find out. So if we do, I think I already applied that to my data set, which is Y. So let's go back. So if we wanted to look at the categories in a categorical variable, of course, we can use the .unique, and that would give us just the name of the categories. And so we see those categories here. But if we wanted to find out what the distribution of those categories are, that's why we use the values count. So here we see for the BMI grouping, we have 4 categories. Now we could do use the label encoder module that is built into Python. So we just load it into our data to a notebook. And once we have used it, we create an instance. We can use it to transfit and transform the feature or the column value, and then we can see how it is distributed. So what it has done, it's converted each of the names of the categories into numbers. So now we have overweight is 1, and normal is 0, and morbid obesity is now 3, and underweight is 2. So that's how that would work. Now, the final transformation is that of transforming, converting the text to a date time feature. So we want to convert the text date to the Pandas date time feature, right? So it's date as the text, and we're going to now convert that to Pandas date time. And for that, we use to_date_time, and we include that column inside of the parentheses as the argument to that function. So once we do that, so it's PD to_date time with the column identified here, and we reassign that back to our data frame. So now when we look at our data frame, and here where we had date time as a float or whatever it was before, now it is an actual Pandas date time object. So those are the main basic types of transformation that you would do to your data set in preparation for modeling. So the fourth step in our data science machine learning project is that of exploration. Data exploration, or EDA, exploratory data analysis, is an extremely important step in our modeling process, right? This is where we get an insight into the trends and the relationships that may exist in our data. There we can find what the anomalies are. We may also do some univariate, bivariate, or even multivariate analysis. And if necessary, where we want to determine a relationship, but it's not an obvious linear relationship, then we would do some hypothesis testing, whether that's between two of the predictor variables or between a predictor variables and the outcome. And of course, all of this is going to involve data visualizations. So this is where you're going to generate your charts and graphs and other types of visualizations that would help you to understand what is the information contained in your data. Because looking at the numbers in data frame, that is generally not going to give you all of the insights that is contained in there. And so we're going to do some of that now. So when it comes to exploratory data analysis, right? So the first thing is understanding the distribution of the values in your variables, right? Whether they are continuous variables, integer variables, so the numerical can be integer or they can be continuous. And then for the categorical, whether it's a binary variable or there are more than two categories. So looking firstly at our target variable, which is CHD, coronary heart disease, we can do a value counts with the normalized equals true, and that gives us a nice table showing the percentage of values or observations in each of the categories. Similarly, we can add the dot plot with the kind equal bar and generate a graph for that. And so we see significant imbalance, which we're going to have to deal with before modeling. But another way we can look at the distribution of variables relative to one of the features. So now we're moving on from a univariate type of analysis to a bivariate analysis. So we want to look at all of the variables as far as sex is concerned, right? So we are going to use the group by method. And then to that, we're going to apply the mean. So what the group by does, it creates a data frame, a separate data frame for each of the categories in a particular variable. So here we have sex, and it's going to divide our data set, our data frame into the two categories and then find the mean for each of those values. So if we ran that, what it shows us here now, we have age and cholesterol and smoking. And so for the gender labeled 1, we have an average age of 40.979. And for the gender labeled 2, we'd have an average age of 40.84. So not much difference as far as the age is concerned. When it comes to cholesterol, certainly there is a difference. The gender age is 1.19, and those who are labeled 2 are 1.07. And so if we just from the fact that there are a higher percentage of smokers in category 1, I'm going to assume those are the male. I may be wrong, but that's my assumption so far. And then there is a 13, as far as smoking is concerned, there's a 13% measure of smokers. And then fasting blood sugar. And so if we can look at all of the values that we have here, and see if there are any differences as far as the gender is concerned. Now, if we wanted to say, just focus on our outcome variable, right, we can just choose that, and that would give us the distribution as far as the gender is concerned. So for 1, there is a 0.04 average heart disease, whereas for 2, it's a 0.0159. So we can, choose other values here to select from our sex group by. But that's how you would do a binary type, a bivariate type of analysis. And you can also plot that as well. If you did plot that kind, let's see, kind equals bar here, that would give you a gender. So now we can see here, as far as the gender is concerned, the percentage of those with heart disease. And that's bivariate distribution. Now, because I had wanted to convert those, and based on what I had seen before in my table, I just want to go back to that to remind me again, and I'm going to remove that because I am saying here that 2 is female. Let's change that, and that 1 is male. And usually there's a info package that comes with these data sets, so you can confirm that. But so if we now, instead of having the 0s and 1, which is good for modeling, but when we want to do graphs and charts, the exploratory type data analysis, then we need to have that labeled. So what I'm going to do is I'm going to create a separate, column, an additional column now for gender or for sex, and I'm going to call this the categorical version. So here I do that, and now if I do my group by again, this time with my new column, then I can see female and males there. And so now what I want to do is generate a plot, and we saw we can do it directly from using Python's syntax. But if we wanted to use the SNS module, right? So SNS allows us to do categorical variables. And so you can use the female, male categories and actually generate a plot. So we have a heart disease, and I'm going to replace this with our new features. I want to make sure that I'm identifying the right column. And so now we can see a lovely graph that shows us the average, what average male percentage of heart disease is relative to the average female percentage of heart disease. So on average, males are 4.5 something percent, whereas for the female, it's probably 1.8% or so. And so that's what that, 1.6 actually. So that's how we would do our bivariate type of analysis in general, right? You can do the group by and then generate a chart or a graph, or select a column in particular, or we can actually use our cat plot where we identify the data frame, then we identify the Y, values, right? So those are going to be what's, is on the x-axis, and then we choose a particular column. So now for the x-axis, and we can see what that looks like. So that's, we can also do things like we can do, instead of just a cat plot, we can do a scatter plot for our variables. And here we're going to have to use, make sure that we're using, continuous variables, even though there's some variables in here that are labeled continuous that are not. So what we're going to do is we're going to go back to our list of variables and at least see. So I'm assuming that this is a continuous variable, and we're going to put that in here, and then we'll choose another continuous variable and we put that in here. And now we can generate a scatter plot for those two variables, right? And so that's what our scatter plot looks like. And I'm going to just kind of make it a little bigger. And for that, I have to make sure that I have the object. So I can do plt.bigger, and then I can do fig size, and I'm going to say 12 by 7 or so. So yeah, so we need to have the equal sign there. You see how it was telling me something is wrong. So now we have that. Now what does this mean? Let's see what happens here. And it is saying that I need another comma. Okay, very good. So now we have our plot, and it's, bigger. And we see we have some outliers here. That's the other thing that data exploration helps you to see, these outliers and these anomalies, right? And so we'd have to figure out how we're going to deal with that. So certainly when it comes to the cholesterol measure, there is an outlier. If we wanted, now this is a bivariate analysis, we can make this a trivariate analysis by adding Q equals to, in this case, we're going to use our target variable. And if we ran that, now we get a plot, and we can see where those who are considered having had the heart disease, how they're distributed. So that's what we would do as far as these things are concerned. Now, so if we wanted to, we could also use the SNS.reg or reg plot. And what that does, it gives us a trend line. So we can see if the variables, the two variables that we're plotting, if there is any linear relationship between those variables. And so that would be this trend line, depending on the angle of the trend line. If it's a steep angle, then we know that there is a strong relationship. If it's a small angle, then there's a weak relationship. If it's a straight line, then there is no relationship. So that's the general gist of doing these type of bivariate analysis for our variables using either scatter plot or reg plot. And then when it comes to the categorical variables, we would use the value count, or we would use our group by. So if we wanted to do a multivariate analysis, Right? So we could separate our data frame into categorical variables and numerical variables. So here I'm creating a subset of categorical variables, and I'm using the select underscore dtypes method. And here I identify the columns type that I want to select for. So when I run that, I get only the categorical variables, or at least those that are labeled categorical variables. And so I can now look at my variables, and here, this is where I am seeing, so we see here that these are the different categories. But if I were to look specifically at the variables that I am now identifying as categorical, so we see those are the ones with only 2, 3, 4. The max here is 7 categories, right? And so these are the original variables: diabetic status, and then 10-year update, and even there's a filter variable created here. And we have these variables. So this was an extra. So they binned the variables. So HDL, they binned into 3 groups, and SBP, the systolic blood pressure, they built into 4 groups, and BMI, they also built into 4 groups. Age, they built into 5. So this is all the variables where they created additional variables. So they did some type of transformation essentially in this data set. And then if we wanted to, we could actually now do some separation of our variables, as far as we can look at, and what I want to show, how we did just the numerical variables. But what I noticed was that there were some variables that were labeled categorical or not, that were labeled either floats, numerical values, that were not necessarily categorical variables. And I'll give you an example. So if we looked at the number of unique values in some of our data sets, some of our columns, for example, smoking only has 2 unique values. That tells me it is actually a categorical variable, but it is not labeled categorical because it doesn't show up when we separate those labeled categoricals from those labeled the not labeled category. Smoking should be categorical, so should sex. It's not showing up here. Of course, our target variable is also categorical. Then 10-year update. There are a bunch of these variables that actually should be labeled as category, or should be treated as categorical. And some of them are, but others, and some of them are, but others are not. And so when we go to do our modeling, we want to make sure that we have transformed the variables appropriately. Now let's look at the numerical values.
Choose from over 300 in-demand skills and get access to 1,000 plus hours of video content for free. Visit SkillUp by Simplilearn. Click on the link in the description to know more.
So continuing with our exploratory data analysis, all right, so we're separating out the categorical variables, at least those that are labeled categorical. But when we do our .unique, for the entire data set, we see that there are some of these features that only have 2 unique set of values that should ideally be categorical variables, and they're not. So what I'm doing here is I'm going to now assign the entire data frame, to a separate data frame based on those unique values. And then I'm going to, give this new data frame, by putting it as using .reset index. I'm now converting it to a data frame effectively. And so that's what it looks like here, except that the column labels are weird. So that's where I'm giving the column labels actual names, features here, and categories. And so when I do that now, I can convert all of the data types to integers, because some are floats, some are integers. But what I'm converting to integers are these values, right? Because I want to be able to sort those values. And once I've sorted those values, now I probably didn't need to sort it necessarily, but I'm now going to create a subset of features that have unique categories less than 10, because those are the true categorical variables. And so once I do that, now I get a list of these columns that accurately should be labeled as categorical. And so now I can use this list of feature name or column names to create my true categorical data frame subset. And so this is what we have here. And so once I have done that, now I don't need to print this out again. So I'm going to delete that. But now once I've done that, now I can use this data set, which is of categorical variables, and I can produce count plots. So count plots is one of the plot type in the SNS module, and that allows you to plot categorically labeled variables, and so you can see what those look like as far as the distribution is concerned. So if we did count plot of this feature, now when it comes to SNS, you always have to do data, and you have to identify the data frame, and then you can identify what the X values that you are wanting to count for, essentially. So now we can generate that count plot, if I spell it correctly, and we can see here a distribution of all of the categories in that particular variable. So most of the data set is made up of those between the ages of 26 and 40 and 41 and 45. So from 26 to 55, that's the majority of, and it gives you an actual count of observations in each of these categories. So now that these are all categorical variables, I can include them in my for loop. So I am using a for loop, and I'm saying for I in, and I'm enumerating over the list of columns. And so when you use the enumerate, it identifies the index as well as the value. So I'm enumerating over this list of columns, and then so for every column name, I will then use that the first object identified from my enumeration, and that's going to be the X. And of course, the data is coming from the data frame. And now I'm using the hue as the target variable, so I can see how each of my variable is distributed as far as the outcome variable is concerned. Now, because there is such significant imbalance, there isn't much to see. When it comes to the percentage of persons with heart disease, it's so low that, you get these very small, very low bars. But that's what you would do. So we can see here for smoking. So if this is the smoking category, these are the people, this is the count of persons without heart disease, whereas those with heart disease. Similarly, so there is not much to see here. But if you had a data set where there wasn't as much imbalance, this would be something very useful as far as the distribution of our variables are concerned. So now we are moving to our continuous variables, right? And so we are looking at those variables labeled floats. And if we generate a subset of the data set, we would get these variables here. Now we see heart disease is still here and some of the others. Now what I could do is do a subset of the data frame that is actually minusing all that I have chosen for my categorical variables. So let's do that. So I'm using the dot drop method, and I'm going to drop all of the categories that I have considered now as all of the columns that I consider categorical variables. So as I do that, now I see that they're all listed as float, but I also want to get rid of this date column because it's a different type of data. So we get rid of that, and now we have some, we have our columns here. Actually, I'm dropping it from this data frame, not the main data frame necessarily. So now I drop that, and apparently it's already dropped from the data frame. So let's see if I ran this again, it is still there. So why am I not able to drop it from this data frame? Siege date, access equals 1. Here we go. So now it's dropped, and now we can do some things with our numerical data set. One of the first things that we could do is to actually generate a correlation matrix. And so for that, we would have the name of our data frame, and we'd use the .core method, and that would give us a nice matrix that shows the correlation between each pair of variable. Now, because it's, not as easy to look at all of these numbers, and this is where the charts and graphs makes things a whole lot easier. So we're going to use a heat map, and that will give us a nice visual as far as the relationship between our variables are concerned. So now I'm going to try to make this bigger by using PLT bigger, and I'm not sure if this is going to work, but we're going to try. I may have to actually do it inside of the heat map function itself. So we are going to do 12 and 7 and see what happens here. Oh, that worked. So now we see our data frame as far as the continuous variables are concerned, and where there is some correlation. Now, of course, this end of the data frame, we're seeing a lot of correlation. LDL is correlated with the variable that's created from HDL. HDL, yeah, so it's also correlated with this variable here, which is the cholesterol. So we have LDL cholesterol. This is a intersection or a bisection variable or a interaction variable that's created between LDL and cholesterol. And so, of course, it's going to be correlated with LDL as well as correlated with cholesterol. So the other variables that it's correlated with, let's see, anything other than those mentioned. Not much happening here. And HDL cholesterol. Oh, so if we look at our legend here, though, light values is positive, strongly positive correlation, whereas the dark values are the negative correlations. And these negative correlations are not more than minus 0.3, so not very strong. So for light correlations though, so we can see that the fasting blood sugar BMI interaction is strongly correlated with systolic, well, let me see, that's about a 7. That's 5. Strongly correlated with, or moderately correlated with systolic blood pressure. Here we have, so there's as far as the interaction variables are concerned, quite a lot. So not much in terms of inferring anything. If we looked at some of these raw values, age is not very strongly correlated with anything. So usually the heat maps are a lot more informative, but in our case, not so much. But we can do some box plots to see how the variables, the distribution of the variables. So for a simple box plot, you would simply do dot box plot. So using the built-in Python plotting. But of course, because the variables are on different scales, it really kind of doesn't show much. So if we do the facet grid now, where we have a separate box plot for each of the variables, and not only do we have a separate box plot, we can also now separate based on additional variables. So we can do bivariate as well as a trivariate type of analysis here. So here we're looking at gender versus age. And so we can get each of the age groups as a separate plot, as well as we can see, how those age groups, the count of the different number of observations in each of those categories relative to the outcome variable. So we have the rows representing the gender. So we have gender in the rows here, and these are the two genders. So we'll have the male and female. So this is sex 1 for this row and sex 2 for the second row. And then for each of the columns now we have age groups. So we have the young people, the 41 to 55 here, and the 56 to 70, and then we have the ones who are less than 25, and then those that are more than 70. So we get an idea of how the heart disease is distributed. Now, mind you, it's showing here, this is 0 and this is 1, even, ignore what the x-axis is. So this would be no heart disease, no heart disease, and so on. And not much difference as far as the gender. It's hard to see anything clearly. Alternatively, we could use the facet grid, and instead of the histogram now, we're using a scatter plot. And so we're looking at these two variables, comparing these, the relationship between fasting blood sugar and total cholesterol. But we're now dividing based on the age groupings. So we have the age groupings here, and we have the fasting blood sugar versus the total cholesterol, and then we have the hue for as far as whether that person had heart disease or not. So that's how you would do some of these bivariate and even multivariate type of analysis. If we wanted to look at just one, just doing bivariate analyses for a particular variable, then we could do that. So here we have the X as the age grouping, and then we have Y as the total cholesterol. So instead of having a series of maps or graphs or charts, this should just be one. So we can do that one at a time. So we create our object or plot objects, fig and x is equal to PLT subplot, and it's determining the size. So when we do SNS box plot, where we identify the X and the Y axis from this data frame, and we say the AX is based on this AX we defined here. When we run that, it gives us this really nice graph where we can see the relationship between the age groups and the total cholesterol in terms of the mean of these values for each age group. So we see definitely that those under 25 had a lower median value as far as the total cholesterol is concerned. And then for the 26 to 40, we see there's definitely some type of an outlier happening here. Now, this is interesting because what it's showing here that there's a total cholesterol outlier, but remember we have different measures for our cholesterol. So if instead of the total cholesterol, we use the LDL cholesterol in that plot and we replaced it here. So what that would show us now is that there is no longer an outlier in this group. So the extreme value is actually the HDL cholesterol, because remember, total cholesterol is the sum of LDL and the HDL. So just some further insights. And then there is this outlier here possibly, but LDL cholesterol, something that you want to be wary of. HDL is the healthy cholesterol. So just some ways you can gain some insight. And then finally, if we were to generate these box plots for each of the variables, we can see the ones. So there we see that total cholesterol with the outlier there. And then if we were to look for specifically that LDL cholesterol, so we see HDL, so there is the outlier in HDL and not so much in LDL. Just looking at it. And so that's what we're looking. So now we've kind of looked at all the ways we can do exploration of our data, whether it's categorical variables using the count plot or numerical variables. We looked at the heat map, and then we looked at some box plots and of course scatter plots. So just some ideas of how you can explore your data. There's a whole lot more to it, but just to give you some idea. So now that we have filtered our data set, we've transformed some of the variables, now we're ready to generate our machine learning model. So when we did our data exploration, however, we learned that our target variable, which is CHD or coronary heart disease, is significantly imbalanced. And what that means is that there are very few observations in one of the categories. And in this case, it is the category of interest, which represents the persons who've had heart disease. So if we do our values count, we see that for the 4,500 or so, only 125 actually are recorded as having heart disease. And if we do normalize equals true, that shows us that about 2.789% or so are those who've had heart disease. So that would be considered an imbalance. And if we were to look at that graphically, we'd see that in the bar chart here using plot.kind equal bar on the value counts. Alternatively, we can do a plot kind equal pi and get a par chart. And I've added the labels here, as well as the syntax for removing some of the numbers after the decimal point. So this is just to illustrate just how imbalanced the data set is. And so we would need to do some kind of bootstrapping, oversampling to balance out that target variable. So before that, though, we first we're going to do a splitting of the data set. So we would normally do two splitting into the X and Y, or the input and output, or the predictors and the outcome variables. And then we would split that into our train and test. So if we wanted, we can do. So here we see what our data frame looks like, and we're using the numerical, the continuous variables, because these are more attenuable to smoting, and we'll learn what that is in a second. But we want to smote this oversampling, and so that's going to be based on the continuous variables. So we've filtered out a subset of those variables, and that is going to be our X matrix, or input matrix, or our predictor variables. So we have the shape here, 4,557 by 18 columns, right? And then, of course, the Y is simply going to be the column with our target variables. So that's going to have the corresponding dimension. It's a matrix, but this one has it's just a series, or just an array, whereas the others, it's a two-dimensional. So we now have our X and our Y. So we can go ahead and smote our variables. And smote stands for the synthetic minority oversampling. And so because our target outcome or category is so low as far as the proportion is concerned, we are going to do a sampling and oversampling, but we're going to be oversampling of the minority set to generate synthetic observations. So that's what the smoting does. So the first thing we do is we load the algorithm into our data set. So we're going to get the smote algorithm from the Learn oversampling module. And so once we have that loaded, then we create an instance of that algorithm, and we assign it to the variable name OS for oversampling. Then we take that oversampling algorithm, it's just a blueprint of the algorithm. So now we're going to use the data to train this smote model and get the features. So we use fit_resample. Now with other algorithms, we use fit_transform. In this case, we're using fit_resample. And the parameters are the X matrix first, and then the Y matrix, or the Y series. And we are going to assign the results of that fit resample back to what would be now our new X matrix and our new Y values created by the oversampling. So once we've done that, we can take a look at the dimensions of these new objects now. For the X, we see it has dimensions 8860 by 18. Now remember, our X was 4557 by 18. So now it's 8860. So we've doubled the number of observations, right? The number of columns remain the same. Similarly, for the X variable, we have doubled the number of outcomes to match our X. And so we can take a look at that. If we did a value count on our Y series here, we would see that it's distributed equally, Remember what the distribution was here? It was 97 to 2.78. That was the ratio. Now that we have smoked the data set, our new ratio is 1:1. So 50% of the observations are those who had heart disease, and 50% are those who've not. So that is what the smoking does. So it has used the minority outcomes and oversampled for those to create synthetic variables. And if we plotted the bar chart here, we see that the both bars are the same using the dot plot. If we use SNS, it gives us a nice colorful plot version. But we can see definitely that the count for each category is identical. Now, if we wanted to look at the distribution of these synthetic observations, we could recombine the X and the Y back into a data frame such that we could do some bivariate and even multivariate type analysis. So that's what I did here. So I've assigned the X matrix to created a data frame with it using pd.dataframe. And this df_os is now the new oversampling or smoked data frame. And then I add the outcome variable or heart disease to that data frame. So now we have a complete data frame, and we can do all the things we did with the original data frame here. So in this case, I'm creating a scatter plot with the data frame, and I'm using BMI. You choose any random, any one of the many variables. I'm plotting BMI versus age, or age versus BMI, because Y versus X. And I'm using heart disease as the hue. So when I plot that, I get this lovely scatter plot here. And what you see is all of the blues are the ones that did not have heart disease. And now the orange are the synthetic, well, mostly the synthetic observations. And so you can see how it's distributed as far as these two variables are concerned. You can choose any of the other variables and substitute. So we can look at, we had age and BMI. We can do fasting, blood glucose against, so we'll just leave the age in there maybe and do the fasting blood glucose. And see, so there we can see how the synthetic variables are created, right? So this is the blue, no heart disease, orange, heart disease. And so some of the synthetic are going over here into this sparse. So that's the general idea of how the smoting works. So now once we have our smoted data set, we can now do our second split, which is into train and test, right? And for that, we're using the train_test_split method, and we're using the X and the Y as the arguments for that method. We identify the size of the split. 0.3 would be the test, and then we give a random state. So when I run that, I get now 4 matrices: X train, X test, Y train, Y test. So we're going to use X train and Y train to train our model, and X test and Y test to test the performance of our model. So before we actually, fit the model, we're going to standardize our data, right? Because these data points or these features we know from when we did the box plot, we saw that the ranges for these values were quite different. For example, the age, of course, is going from 18 to 70 something, but you have things like blood pressure and others going up into the hundreds. So in that case, if we were to plot just the head values here, just to see what that looks like, right? We can see age, right? So that's kind of the range. Maybe if I did a dot describe, that would actually give ranges. Yeah. So age is ranging from 19 to 83. But when we look at some of the other values in our data set, for example, blood pressure is going from 70 to 196. Blood sugar is going from 54 to 404. Then, of course, these interaction variables that are created by combining two variables together, they even have a wider range. The glucose BMI interaction, it has a maximum of 16,000. So the range is different. So this is why we are going to scale our variables and to make sure that they're all in the same scale. So we use the standard scaler, and that's going to convert all of the values to their z-score. So the values are going to be in standard deviations, essentially. So we create an instance of the standard scaler, and we fit that on the train data set. And once we fit it, we can then transform all of the variable based on those the values in our standard scalar model. So this is what our values now look like, right? So we have values going from, in this case, the columns headings are missing, but you can see there's minus 1.8 and there's 3. So the values are all in standard deviations, right? Now, either 1 or 2, in some case 3 standard deviations above the mean, or 2 or 1.5 standard deviations below the mean. So the range is now much smaller. So now that we've scaled our variable, so we have this x underscore train underscore sc for standard scale. And now we can use that in our model. So we are going to do a logistic regression model. Remember, because our outcome is categorical. So we're generating a logistic regression model, and the logistic regression model is going to do a classification of yes or no, binary classification, 0 or 1, heart disease or not. So that's what the logistic regression is going to tell you. Now there's a lot of some math and some integration involved, but just understand that it's doing a classification. We have identified the solver here as the liblinear, and we generate an instance of the logistic regression model. Once we've done that, we can use our data. Now we're using the X train scaled and the Y train to fit our model. So let's run that. And so now we have our model, and we can test the performance of our model. But now, instead of the train data set, we're going to use the test data set, right? Because we don't want to test the model on the same data that was used to train the data, right? Because, we're going to get elevated, performance and not accurate indication of how well our model will generalize to data that it has not seen before. And that's the whole idea. So now we are going to use the test data set. But remember, this model is built on data that has been scaled. So we have to scale our test data as well. So we generate another instance of the standard scaler, and we train it on the test data set. We don't want to use the same standard scaler that we trained with the train data set, because that's going to cause data leakage. And so the features of the scaler from the train model are going to be slightly different. So we want to treat this test data set as data, fresh, new data that's coming in from who knows where that we've not seen before. So is going to be subject to its own set of values and inputs. And so we are going to standardize and get new features for a scalar, and then we will transform the test data. And once we have that x underscore test underscore SC, now we can use that x test scale and our y test to test the performance of our model. And what we do is we do model name dot score, right? So this is one of the attributes that are built in with the logistic model class, and we can apply that directly to our model. And as long as we put in the x values and the y values, it is going to give you a result. So what it's going to do is it's going to take the x test values and put it into our model and generate results. Those are going to be our predicted results. And then the algorithm will compare how many times the predicted results match the actual results in the y-test data and give us an accuracy score. And so that's what the results are. And we multiply by 100 to get 100 to get the percentage. So we run our model, we do the X test, and then we get the score for our model. So now we can use the X test scaled and the Y test to test the performance of our model and see what the accuracy percentage is. So in this case, it's 76% accurate. If we compare that with the train data set, we see that it's 77% accurate. So not much of overfitting happening. But those are the results thus far. This is our base model. Then in the next video, we're going to look at other ways we can test the performance of our models using other metrics, and then even maybe some ways of improving on the performance. But the general idea is you would get your data, you would separate the X from the Y, as we did here. We had separate X and separate Y, and we then smote our data set. If there is imbalance, you smote. If not, you just move right on to separating into train and test. Once you've done that, you scale the X train data, and you use that to fit that instance of the model that you generate. So now you have your model, and once you have your model, you can now test the model, but you've got to scale the X data. Whatever you did to the train, you have to scale, but with a different instance of the standard scalar. And you then now use that scaled data to test the performance of your model. So when we did our last version of the model, this was the accuracy score, 77%. So meaning every time we made a measurement, we generated a prediction using our model. 77% of the times we were correct. The other times we're not. So we want to see if we can improve on that accuracy score somewhat, right? So remember, these were the values, these were the features we included in our model, the ones that were numerical, float data type specifically. And these were the categorical variables that were left out. So what I did was I'm going to add some of these variables that I think will make a difference in terms of the performance of the model. So I think gender is important. I think diabetic status is important, as well as smoking status. So I'm going to add these back to my working data frame, right? Now, when I do that, I'm going to notice that at least one of them is categorical. So we can't use it in the model in that data type. So I am going to, so this is how it's distributed, non-diabetic and diabetic. So it's, categorical with text labels. So what I'm going to do is I am going to change that, and I'm going to replace these text labels with integers, right? So now when I do my info, I will see here that indeed my diabetic status is now of data type integer. And so I can use it in my model algorithm as such. But before doing so, I want to generate a plot of the correlation between each of these features and the target. Now, this is only going to look at linear correlation. And so it's, just kind of a measure. And the graph is generated showing the different features and how they are contributing, the correlation between the target, right? So we can see age is very strongly correlated, whereas LDL cholesterol is not so much. HDL cholesterol, on the other hand, this is strongly correlated to not having heart disease, whereas age is strongly correlated to having heart disease. So as the age increases, the probability or the likelihood of a disease increases, whereas as the HDL increases, the probability of heart disease goes down. Systolic blood pressure is strongly correlated with having the disease, and so on. And sex, going from one sex to another, there is a stronger possibility, and I'm going to assume that that's going from female to male. There is a stronger likelihood of heart disease. So I want to include these measures, namely gender, diabetic status, smoking. So that one is not as strong as these two. So hoping that by including these three variables, that we would get a higher accuracy, right? So now we have a new data frame with the additional columns. So instead of the 19 that we had before, 18, 19, we now have 21. So then our Y value is still the same. Then now we can smote. We're going to do that oversampling of the minority again. And we are going to use that. Also, I did not load my smote algorithm, and let's go ahead and do that. It is inside here. So I've done that. So now I can go back to my smoting, and I can then create that instance of the model and generate my new X and my new Y. So now with the new X and the new Y, I can now separate. So remember there are two divisions, separating into X and Y, and then separating into train and test. So now we have our new train and test based on our new X and Y. So now we can model. We create an instance of the logistic regression model using the same solver again. And then we use this, this is our new model, framework, is the blueprint. But first we have to, of course, scale our data. So we using the standard scaler here, and we create scaled versions of the X and Y, just to show you what that looks like. So now we have these values. Instead of age of 50 or 70 or something, we now have them in terms of their standard deviation, or their z-score, I should say. And so now we take these new scaled X trains and the Y train, and we fit the model. And now we are going to test the model. And this is my test for the model. I move that up here. So we're using the test data set. Oh, that's why this is here, because we need to scale the test value. So we fit our standard scalar on the x-test, and then we transform all of the values. So those values now look similar to what the trained value, x-trained values are. And now that they're more like that, now we can put that into our model and we can generate our score. Not much of an improvement. It went from 77 to 78. And as far as the training set, yeah. So not much of an improvement here, but, we added some variables that I thought were important. Didn't prove to be so much. But we can now look at some other things we can do as far as our model is concerned using some different metrics, right? So we're going to do some cross-validation. And remember, cross-validation is where we are separating our model, our data set into test and train, but doing so several times and changing what values are in the train versus what's in the test. So we're kind of mixing things up, as it were. So we need the k-fold algorithm, and we need our cross-val underscore score to use for the cross-validation. So we're going to divide the data several times over, and then we're going to test that the model each time and save the score and then find the average. So I wanted to show an example of what happens with the cross-validation, right? So if this is our data set, we would divide into the train and the test, and we would use this proportion of the data set to train the model, and then this proportion in the yellow to test the model. Then the next iteration, we would reserve a different set of observations for testing and use these in the blue for the training. And then we would change that, depending on how many folds we have indicated in our data. So that's what that is. So we have the k-fold and the cross-val that we are loading in the data set. So now we create an instance of the k-fold. We state how many splits we want. So here, this is 10, this is 5 splits. We are using 10 splits. The splits, of course, the more splits you have, the more times you will be running your training. But you also have to take into consideration the size of your data set and how long each of these trainings are going to run and how much computing power it's going to utilize, and different factors. So we are doing 10 splits. So instead of 5, we'll have 10. And we're creating a random state. So if you want to repeat what I'm doing, you use the same random state and should get the same values. And then we are saying shuffle is true. So we're changing around how the data is being split every time, right? So that's what that does. So we now have our k-fold, and then we have an instance of the logistic regression model. So now we're using our cross-validation here, and we are going to use the model that we created here, and then we're training it on the X train and Y train, and that should be our scaled data. And we're using the Y train, so X train scaled and Y train. And then for the cross-validation, we have this k-fold object that has all the information in there. So when we run that, we are going to get a set of values. So we ran 10 different models, and each of them had a different accuracy score, because that's the default metric that's being used. So some had 77.9, others, one had 80, and then one had 76. So the values are between like 75 for the lowest accuracy and 82 for the highest accuracy. And on average, it had a mean of 78% accuracy with a standard deviation of 1.86. Now, we can use a different scoring method other than the default accuracy. And here we're using the negative log loss. And we can run that with the same parameters. And here we see that the average negative log loss is negative 0.47 with a standard deviation of 0.18. So that's another way of, measuring the performance of your variable. And you can then make changes and use the same kind of cross-validation again. But we can also change it to the ROC AUC, or area under the curve method of estimation, because this is a logistic regression, and accuracy is generally not the best method for assessing the performance. So if we use the ROC AUC, so now we're creating a different model here, we're training it, and I'm forgetting to make sure that this is the scaled version of, what am I doing? The scaled version of my X train. So let's see if that didn't make much of a difference. But here we have the X train and the ROC as the measure. And so it's given an ROC score of an AUC score of 86%. And so we can look at that to see what that looks like graphically. So we're going to use the confusion matrix and the classification report. So the confusion matrix, that is the matrix that gives, so I should have those in there and make sure that I have one of these models as I rightly called them. So after you've loaded the confusion matrix and the classification report, you can use them for different representations of the different types of metrics that you can use with your logistic regression to evaluate the performance of your logistic regression. So if we did the confusion matrix using our X test and the predicted Y meaning the values we would get from our model if we put in the test values or the values from our test data set that's been scaled. We get a set of values and we use that to compare with what the actual values are in the data set. And we use it to generate a confusion matrix. And this syntax here is what is going to allow us to view the confusion matrix as such. And so we have our true positives here and our true negatives, and we have our false negatives and our false positive. So we can see where the model is doing well and where it is not. And so this gives us a further insight into our model's performance. And so we may care more about one type of performance in terms of whether we care more about the precision or the recall, or maybe some balance of both, right? And so we want to make sure that we're doing that. And when we have this confusion matrix now, we can see where we are. Now, in addition, the precision recall, we can also get the F1 score. So we use the classification report, again, with the Y test, which is what is in the actual data set, and the predicted values. And so we can see what the precision is and the recall is for the one category of the data and the same for the other category of the data. And then, of course, we have the accuracy score, and then we have the macro average and the weighted average. So that's what the the classification report will tell us. And finally, if we wanted to look at the list of features and in terms of the feature importance, so what we do here is we are first going to get a list of the features names from our column, right? So now we have the names of all the features that are included in our model. Now we also can generate the coefficients for each of these features in the model, and we're using LR1 in this case. That's our model. And so this is the list of the coefficients that correspond to each of these features. Now, to combine that into one data frame, right? So firstly, we are going to convert those coefficients into an array, then into a list as such. And now once we have that list, we can use those two to the features and the coefficients, the names, create two dictionary items, right? And that's what we're doing here. And then we can change that into a data frame, and we will sort that by the coefficient values. So this is what it looks like here. And so we see that glucose is the glucose blood pressure interaction is the strongest. Now it's kind of hard to see all of them here. So then of course we can, now that it is in the form of a data frame, it's easy to plot that as a bar chart. And so I plotted it as a bar chart, and then I've used the names of the features as the X tick labels, and this is what you get. So here we can see the contribution of each of the features to the model's performance. So age is the strongest, in this case, negative indication, meaning that as age increases, you're more likely to have a cardiovascular disease. So similarly, the LDL cholesterol interaction and HDL cholesterol interaction, those are strong contributors. Then we have here, and I don't know why I have limited this to 17. Let's change that so we can get the names of all of them. So now we have sex as being possibly not the strongest. So one of the strongest. Age, it seems, is the strongest contributor to heart disease. Diabetic status is also a strong contributor. Smoking is a strong contributor. Now, remember when we did the linear correlation, it was not, because the correlation between smoking and heart disease apparently is not linear, but it is strong. And then fasting blood sugar BMI and fasting blood sugar systolic blood pressure. So that's how you would do that. So remember what I did? I simply added back some of the variables that I thought that might have been important that got left out. So I added smoking, diabetic status, and sex, and I didn't get much of an increase in the accuracy of the model, but it did increase. Now, we didn't measure things like the precision and recall prior to adding those. So we don't know what those changes might occur, as far as it's concerned. But we did the cross validation tenfold, and we got the average values. We also got the net neg log loss. We got the ROC AUC score, and we generated the plot for that, as well as the classification report. And then finally, we did a table of feature importance that we plotted on a graph. So that's how you would do your model optimization. So you can keep on further tweaking and optimizing your model, adding some more variables, taking away others. For example, like we could probably lose some of these features here because they don't seem to be contributing much to the model's performance, and just keep testing it and see what happens. But that's it in a nutshell, how you would do that. Now, there are other types of models besides the logistic regression, and maybe the next video I will do a decision tree or a random forest and see how those perform. But that's it. So I hope you've enjoyed watching. And if you want to know more about how these model machine learning algorithms work, remember to like and subscribe.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.